2021 was finally when we first published our results.
Results from a laboratory in Illinois suggest that there's new evidence from the behavior.
Fermilab's Muon g-2 experiment.
This experiment at Fermilab in Batavia.
It's called a muon.
Muons?
Muons.
Muon is basically a heavy electron.
Muons, they have a small hole.
Oh, that's a cool little tune there. But apparently Fermilab has released new results since 2021 for the next couple of runs of the Muon g-2 experiment. And yeah, they hit 5 sigma. Well, why the heck am I here? You could hear that from anybody. Oh, wait a second. Oh, it actually helps when I actually show the thing. What's the thing? Oh, I think you all are going to like this. Oh, another crazy equation. Thank you, Ramanujan. You left us too soon. Well, you all know what that means. We conjecture ahead.
Although this is going to be weird, and it's going to be about a different.
Title of the conference was something like "Ground Truth" or "Turtles All the Way Down," and so it seems as though there's one Ruliad. I don't think it rules them all, and it might be just hyper-rulial turtles all the way down.
Yes, it's on the back of an infinite number of hyperrulial turtles.
Various people are commenting on the outrage of hacking the universe on a MacBook Air.
Hey guys, what's going on? Memes here, yes. I apologize. I had meant to do this yesterday. Ran into a little kerfuffle. To be fair, full disclosure, the more data we get, the better measurements we get. That's how we better fit the models, because we want to connect it to reality, right? Isn't that what Professor Feynman said? So what are we talking about here? Basically, this is what first actually got me into this. I'm hearing like the Muon g-2. I'm going into the science realm. I'm like, all right, this is cool. I guess this is a big deal. I also happened by chance to come across Thad Roberts, the founder of the physics monastery. Yeah, and essentially, as far as I could see, he's the only person that actually like nailed the Muon g-2 results. I'm just saying, but this was actually the result that was published in the second edition of 44. I believe there was another one before that. We'll get into that. But we got this crazy thing right here. What is this crazy thing right here? Okay. So as we've been over on this channel, we utilize the universal binomial factorization equation. What's that? You take your dimensional ingredients, which are your boundary conditions. You multiply them by a primary action. Primary action might be 1. Maybe it's 2 pi. Maybe it's 4 pi. We tend to interpret that as like a circle or a sphere, typically. Now, and then we multiply it by the terminal action, because usually right around 7 significant digits things, they seem to get a little wonky for some reason. Also, coincidentally, 10 to the negative 7 happens to be the result when you multiply the Planck mass by the Planck length and divide by the Planck charge squared. That's a pretty neat thing. I believe it's magnetic permeability. I guess that's an important thing. Rumor has it. Oh, hello, Tim. Thank you for joining us from the Raylo realm there. Yes. That's exciting stuff. But again, it's like, I want to make sure I'm bringing, and to be fair, I'm not even sure if this is the final form. Probably isn't. We have some better measurements. We can hone in a little better. Maybe I'll do that live at some point. If that hasn't already done it already. But okay, so what are we talking about? All right, let's go to Fermilab. So our friends at Fermilab, basically they confirmed the previous results, and it looks, I think they had an extra significant digit or 2. I think I might be wrong about that. All I know is the error bar shrunk by like 1/4. Like that was the big thing they were structured. It's like, yes, our error bars that we have here literally just went down. I think they replaced one of the things that was potentially heating up there. And the experimentalists that are out there, like, they do some absolutely crazy stuff, man. Hey, fist bump to them. But let's not belabor the headline. Muon g2 doubles down with latest measurement, explores uncharted territory in search of new physics. I mean, is it new or just we haven't really discovered it yet? To be fair, they hit 5 sigma, which within, I believe, particle physics, that's when they typically accept a new discovery, because the chances of it being just a statistical error, about like one in a million or so. That's not too shabby. So physicists have now have a brand new measurement of a property of the muon called the anomalous magnetic moment, and proves the precision of their previous result by a factor of 2. An international collaboration of scientists working on the Muon g2 experiment at the U.S. Department of Energy's Fermi National Accelerator Laboratory announced the much anticipated updated measurement on August 10th. That was yesterday. This new value bolsters the first result we announced in April 2021. That was on April 6th. I remember that because that was one of the dates that was in the video, because on April 7th, I tweeted at Adam, like, I'm not sure if this like helps your model, but does it? He's like, yes. And that was how I went down this rabbit hole, or Wolfram hole in a lot of circumstances. But so what are we talking? Let's do this. Let's get the old stuff, some old housekeeping out of the way. So we're gonna go back to another video. So this is actually from my Pace 1 entry to Mr. Kurt J. Mungle. Shout out to Kurt's Pace 1 contest from last year, where we received an honorable mention. Thought that was pretty cool. All right. So links on the doobly-doo. I forgot, I think, 1 or 2 links to like the hyperbolic vortex equation that's in like most of the other things. I can add that later. For those of you interested in perhaps exploring reality, I claim. But let's go right here. Oh, let me make sure we have the sound, because I don't want to be that noob. Okay, there we go. So we've got some sounds. Let's go.
Remind you, this is our Mars rover moment. 10 years, thousands of people, years of effort, suddenly in one moment being revealed to the collaboration.
April 7th.
And lucky for you guys, you get to see that moment because we recorded it.
The number we had predicted is right here.
At least on the internet. I hear that's how it works, because everything's like time-stamped and dated. I apologize.
Safely right in the experimental average. Right? Beautiful, beautiful. And more important, notice I give a little thickness to the line there just so you can see where it is, but that's a line with no thickness. That's an exact geometric prediction out to any.
So this is
you want, okay?
Okay, so that's the whole thing, and I think this has been happening in string theory a lot recently. It's like, rather than necessarily trying to like quantize gravity, which cannot be done. I don't know. I've seen some quantified calculations from gravity on this channel. Are they right? I don't know. I guess experiment's going to have to see. We're going to need more observations and see if it matches the predictions. We'll see. But over here, the standard model, it's like the whole thing is okay. It's spinning around. It's doing that. And muons don't live for like a really long time. They only live for like, what is it, like 5 millionths of a second? But within particle physics, that can actually be like pretty long. So they can spin it around that like 50-meter ring like a whole bunch of times, and it's kind of wobbling a bit there. And the standard model initially, you're like, all right, it should be like 2. But since there seems to be some deviation, that's why we call it the g-2. Apparently it's that for the electron as well. But essentially there's actually a deviation here from the model itself. So basically you can see over here, that was on, I believe, from source code 7. It was 3/18/2021. Fermilab released their results on the 7th of April 2021. Happy coinky dink, let's say. But yeah, basically that was using another equation. It seems to have gotten a little bit simpler, perhaps. That's why I'm like, might not even be the final form, bro. So I guess we're gonna have to see. So let's go back to our other stuff and things, because people are like, we needs the receipts. Let's take a look at some receipts. Okay. So this was All right. So that book was published after this one. This one, I have the other one somewhere. This was published in 8/8/2021. Let's do this. So I think this was oh god. Yeah, so next one was a little bit after that. I believe it was early 2022. And we're in 2023. So yes, as I'm boring everybody on my little stuff and things. Okay, let's go back here. For those of you interested. So again, utilizing the universal binomial factorization equation. Okay, what are our boundary conditions? There is conjecture around here. That's why it kind of seems weird. The current boundary conditions for this one, because a lot of this we're fitting the model based upon our best interpretation. You also want to have basically more or less the same primary action because it wants to mirror the electron to like, I don't know, 5, 6, 7 significant digits, something like that. Okay. So the muon G factor, which is G sub mu. We set that equal. It's going to be negative because we're doing the whole -2 thing. So negative square root of B. What the heck is B? B is our break and scale symmetry times B7. Because if you're going to divide a circle, you could have 7 equally sized circles to take up that area, and they're all kissing each other because circles like to roll together sometimes. We multiply that by CR1 squared. What the heck is CR1 squared? That is Ramanujan's first continued fraction constant. CR1 equals 1 over 1 plus E raised to the negative 2 pi over 1 plus E raised to the negative 4 pi. And you just keep on going up by circle, 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 circle. That's pretty neat. We multiply it by this crazy thing here. That's what we call g-1. What's a g-1? That's the first answer to the hyperbolic vortex equation, which I forgot to add here. I actually labeled the other things and stuff too this time. But basically, when you square that, we get what we colloquially call the fine structure constant to basically all the uncontroversial digits. Again, full disclosure, there was a Harvard study a couple of years back where they thought the last digit, instead of being a 7, was a 6. Apparently, they were going to redo the experiment, change the ages. I need to follow up, see what's going on in that. So again, full disclosure. The claim is when you square g-1, we get what's known as a fine structure constant. Or at least the first fine structure constant. Apparently it has 3 sisters, so who knew? The boundary condition here is the mass of the neutron divided by the mass of the muon. Why might be that? That might be the case. My generalized interpretation saying, all right, you're going to try to find out what's going on with this mass. It's like, well, what's something you can balance out, even though apparently I think the neutron has a G factor too, which is kind of interesting, but it's a neutral particle. Science is fascinating. And then we multiply that by our terminal action here. So this is our primary action. This thing over here. Multiply by our boundary condition. We multiply it by the terminal action. That terminal action is 1 plus the secant of the cotangent of 2 gamma n. What is red n? Well, that's 5 because we have 5-dimensional ingredients. Time, space, charge, mass, and temperature. When you go down the Wolfram hole long enough, one starts to notice that the constants of nature as we know them can be made up of 5-dimensional ingredients. Now, there might be current, there might be like acceleration, this or that, but when you play around, you realize you can do it with 5 of them. Might be a complex, fairly, like the Boltzmann's constant's got like this, that, temperature, and all that jazz. It's fairly complex, but again, still 5 ingredients, which is interesting. And then we take that 2 gamma of 5. We divide by our break and scale symmetry again, 7. And then we multiply that by the inversion point, which happens to be the Planck mass times Planck length over the Planck charge squared, which happens to be that 10 to the negative 7. That's interesting. So what happens when we plug this all in? Okay. So I tried to, I couldn't find the combination of magic words to just have Wolfram Alpha plug in Ramanujan's first continued fraction constant. Yes, they say it like twice there. So what I did was we broke it up. Because when is it? When you go over... okay. So we got that 1 over 1 plus that e to the negative 2 pi to the negative 4 pi. Comes out to be this number here. You can express it as e, the base of natural logarithms raised to 2 pi. Oh, look, divide by 5. That's nifty. And then you multiply that by the square root of the golden ratio, which is also multiplied by the square root of 5. Subtracting out the golden ratio gives us this here, 9981. So what happens when we just throw that into Wolfram Alpha? Okay. So this is how we got it to come out before. Because when I basically search that, you get that 1 to that. So basically you need to raise that to the negative 1. I want to get the 1 out of the numerator because I was a noob. So, oh, it also happens to be a transcendental number, which is neat. So you click on that number, gives you this number here, and zoom in. All right. Oh, wait, CR1? Wait a second. CR1 squared. Wait a second. What is that thing? I think you all know. I think you all know. Yeah, CR1 is Ramanujan's first continued fraction constant. Yeah, I didn't just make that up. Maybe it's something Wolfram Alpha. I don't know. So we got that. I expressed it as where are we? It's expressed as this. So I just threw that. So it should be a little less scary when you see this thing and say, okay. The negative square root of 7. Okay, we kind of figure that out. It's like, all right, that's some of us, we've been blessed enough to learn some of that. So it's like, all right. But then you see this 1 over 1, this and that. That's just Ramanujan's continued fraction. We square it there. We multiply it by our g-1. That just happens to be the number that comes out. Multiply it by the boundary conditions again. This is the mass of the neutron. And this is the mass of the tau. I just typed that in. I still need to actually do that. There's a bunch of derivations I was kind of scared of because I hadn't done them before. And it's like, oh, let's stop being lazy and actually do them, right? Savvy. Oh, and this is the 1 plus the secant times the cotangent times that 2 gamma of 5 divided by 7 times 10 to the negative 7. You can just divide by 10 to the 7. What does that give us? That gives us this result right here. What we got? So minus, because we have the minus 2 in here. Negative 2. The digits we're looking for 0, 0, 2, 3, 3, 1, 8, 4, 1, 2, 4, 3, 3, yada, yada, yada. Since it's a geometric derivation, you can go as many significant digits as you want. Again, is this a final form? I don't know. You're going to need more and more measurements to see. And apparently they want to get 2 or 3 more significant digits, which is fantastic. Go Team Fermilab. So let's go back to our friend, Fermilab. So they got the results. They published a paper. Maybe we'll get into that at some point. But what we're looking for here, okay, the new experimental result based upon the first 3 years of the Muon g-2 collaboration is, all right, g minus 2 equals. So you could have that negative 2 there if you want. So the numbers we're looking for, it's going to be starting after the 0, not 0, 0, 2. Okay. 0, 0, 2. 3, 3, 1. 3, 3, 1. 841 841 10. Huh? 2, 4. You are off means that is correct. We are off. This is why we have error bars. Some of that Professor Keen's like, well, we don't really hear people talk about error bars. I think these are supposed to be our guidelines for what we're trying to figure out, and especially with the redefinition of certain things. And you're like, wait a second, the radius of the proton just it changed by how much? Some things we're a little more sure of than others. But hey, Jelly Duck, they're supposed to be within a statistical range, Jelly Duck. Here's how it works, because when we scroll over, I did also have that hidden. So the statistical error, so basically it goes through 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So we should have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. I actually even counted before. Just because it's like everyone's, basically it shows the statistical deviation plus or minus for the last two significant digits. So this is about half the error before. I think it was like 83, 85 or something before. So it's literally half for the statistical. And for the systematic error, it's 19 for the last two significant digits. Okay? So what happens for the statistical error if we go up to, and we add a 4, 3? Well, that would make that a 1. Excuse me, that would make it that a 5 and a 3. Okay, so let me double check. 4, 1, and the last, so that last two would be a 5 and a 3. 4, 1, 5, 3. Okay, so that would be greater than it. And if we were to subtract it, so that would be less than that 1 there. Oh, well, that's a 2, so it's going to be less than 1. Well, that seems to fall within the statistical error. How about the systematic error? 19, a little over 20. Okay, oh, wrong thing. Apologize. So we got 19. So that would turn that into a 2 and 9. Oh, 2 and a 4. Well, that's within the upper half. And if we subtract 1, that would bring that down to a 0. And that's not a 0, that's a 2. My friends, this appears to be a geometric derivation of the muon g-2 results. Technically, it's also a prediction. So again, it's the same thing that was predicted first. So I'm still going to say it's 2. You could try to say this is now 3 more confirmed predictions than string theory, but doesn't mean it's right. But perhaps it may give us a little bit of insight to what's going on in our realm of persistence. Hey, thank you for joining. Wow. I see you there. I see you there. No, this is interesting. And again, full disclosure. Is this necessarily even the final form? I don't know. All I know is, thank you, Ramanujan. You totally left us too soon, but seems like your work is still producing some results. But yeah, that's all we got for right now. Take care of yourselves, everyone. Hey, I thank you for joining T Carr. It's exciting stuff going on here. And again, I've seen different formulations of this. This is just from Thad's most recent or published work from like last year. So the second edition of 44 is what has this actual equation in it. But yeah, some very interesting stuff going on. Again, we're going to have to see what happens. I've heard some other folks say, well, depending on how you analyze the data, there isn't even a deviation. Some of the media is like, oh my God, it's like a totally a fifth force, bro. I'm paraphrasing here, but it's like, and then like the Nature article's like, yeah, no. There's a deviation. There's stuff going on. Okay. Here's at least one model. Happens to have a prediction. But dude, Ramanujan did so much in his life. It's ridiculous. I think he was only like 30 or something years old. But hey, thank you for joining Dan at the last moment. But that's all we really got for right now. Anyone interested in any of the stuff, we got links on the doobly-doo. Feel free to explore for yourselves, because again, rumor has it 2023 is the year to see. So take care of yourselves, everyone.